So let's go to a bit of a review about audio and voltage systems. So audio is considered low voltage system if the voltage is going to the speakers is below 70 volts. 70 volts, you don't need a license to build a system. For example, a lot of the PA systems where somebody can actually announce from a central location, those are low voltage systems. Or in a shopping mall that plays music, those are low voltage systems. They're safe most of the time. They're pretty low voltage. You don't need a license to, somebody can hook it up without having a license to do so. High voltage systems, on the other hand, are 70 volts and greater and can be dangerous. So you need a license to be able to install them, and they can potentially actually really hurt you. Because voltage, when it gets up to a certain amount of voltage, means there's a lot of pressure pushing electrons through whatever it can push it through, whether it's a wire or whether it's through a human body. So we'll talk a little bit about, actually maybe now is a good time, about safety. The way that it works is that a potential is a potential. So I don't know how many people have had those 9-volt batteries. The guitar players, I'm sure, have all had those 9-volt batteries in their foot pedals, right? And to test it, to make sure it's working, you touch it to your tongue. And if you feel a tingle, yeah, that's good. It doesn't hurt you because 9 volts is pretty low voltage, and the battery doesn't have a lot of electrons to push through, so the current is pretty low. So it really can't hurt you, but it can give you a little tingle. How many people have accidentally taken a knife and stuck it in a toaster to get a piece of toast out? Anybody? Okay, I'm the only stupid one then. So I've done that when I was a kid, and your hand goes, oh, and you start getting like, it's not fun. So it can be pretty dangerous, right? The higher the voltage, the more danger there is, because the higher the voltage means how much more pressure there is if you connect with it to push electrons through whatever it can push it through. And it doesn't have to be a wire. It can be my body, it can be my finger, it can be my arms through my chest, where my heart is, and really mess things up. So let me tell you another little story. When I was a sophomore in college, I took a year off so I could play music, and I'm from Chicago, and so I played the clubs, and it was a lot of fun. I had a part-time job at a place called Underwriters Laboratories. Underwriters Laboratory actually tests for safety. They put a tag on the cord of almost every device, whether it's a refrigerator or a fan, and it says UL approved, meaning that they've tested it and it's safe. So you can't get electrocuted from it. And they test it in all different conditions. We had this huge factory-looking place. They had a room that was a sunroom. They had a rain room. They had a snow room where it was all refrigerated, and you'd put like amplifiers in the rain and then take them to the snow room. And you'd move them around to different environments in case somebody left a piece of electronics gear outside. They wanted to make sure that when you touched it, you weren't going to get electrocuted by it. So it was a very interesting place. It's the kind of place where they test refrigerators. The doors are opening and closing. It's like you think of testing factories. So it was really fun, actually. At Christmas, we used to pop popcorn, so we'd have barrels of popcorn, testing popcorn makers. But my job at one point was to test circuit boards, which is these thin little wafer boards that they mount all the electronics on. And my job was to see at what voltage would current actually go from one side to the next, because they're insulation. They actually resist the current flow. And so I built this machine. It was my responsibility, of course, to build the test devices. So I built a machine that had one probe like this, and it had a big copper electrode in the center, and it had rubber around the sides so that it would be an insulator. And then another electrode here, big copper electrode with rubber around the sides, so no current would go around like this and connect. And then I'd stick the circuit board in the middle here, and then I would go out here. I had a meter. Plus, all of this was in protective cage. So I'd have to walk in, set up my test, walk out. Then I'd turn up the voltage, watch the meter, and see how high the voltage got before this thing went through and sparked through, and then the whole system would shut down. So I'd have to step outside and set it up, and step outside, make my test, make my notes as to what voltage it broke down at, go in, take apart the electrodes, take out my circuit board, put another one in. I was doing this endlessly, it seemed like. Hundreds of circuit boards to test, different types of compounds and so on and so forth. And I just got bored after a moment, and so I stayed inside the cage and reached around and did the thing, right? And of course, they would break down at 50,000, 100,000 volts. So we apply a huge voltage potential between the two, and then it would spark through. So I'm standing inside the cage, and at the time I had a pocket watch with a chain. I know you know where this is going, right? So I was just being lazy, not walking outside the cage for safety, even though we were testing for safety. I was just, a sophomore in college. And so I'd, reach around and turn up the voltage. Okay, that's done. And so I could go faster. And at one point I reached to the wrong place, touched the wrong thing. Current went through my hand, down through my belt buckle, to my chain on my pocket watch, which touched ground, and I became a conductor for the 50,000 volts. It wasn't a real fun experience. It was like being hit by lightning almost, except lightning's more voltage. I was thrown against the cage, and I'm like, okay, I'm not doing that again. Taking a few days off. So needless to say, I was pretty lucky. I'm lucky to be here talking to you about it, because if there was more current with all that voltage going through me, I would have definitely died. And the reason you die is because all of that pressure of electrons flowing through your body at some point, your body acts as a resistor, and because the electrons are flowing because of so much pressure of voltage pushing them through your body, the resistance becomes friction of the electrons moving through your body, and you burn inside. Your organs burn up. So when they talk about a guy going to the electric chair, he's going to fry, That's actually what happens. So because of the heat of all of the electrons flowing through your body, and not only the disruption of your nervous system, but not to get too gory, I just am trying to warn you against high voltage and touching anything wrong. So you got to be careful. And part of this week that we're talking about electricity, we'll talk about how gear manufacturers, computer manufacturers, phone manufacturers actually design for safety, because they don't want anybody to be shocked or even get any stray electricity. So sometimes there's a confusion, but alternating versus direct current, let's talk about that for a second. I know it's a band, AC/DC, but it's different. Direct current, alternating current, AC and DC. Direct current is a positive potential that's a steady potential that doesn't deviate from its voltage. So what would be something that uses DC power? A battery, your iPhone, a flashlight, they use DC. AC is an alternating current that fluctuates around a center point. Let me give you a few little pictures. That's DC, so there's a steady voltage and a steady current. AC is an alternating current. So where's AC found? AC is found out of the plug in the wall, right? That's 110 volts AC. In other countries, it's 240 volts, 220 volts. In Japan, I think it's 100 volts. Every country has its own little standards. We adopted 110 volts as being our standard here. And it alternates 60 times a second. Is there a reason? Yes, actually there is. Okay, let's think about it for a second. If we talk about voltage and current, and a direct voltage being a direct pressure on the electrons to move through a wire, and let's say we had 100 volts direct of direct current, it would be much more dangerous than if we had alternating current. So as we discussed before, every wire acts as a resistance to the current flow. So if we had a direct flow, you'd generate a certain amount of heat distributing power, say, from the Hoover Dam to Los Angeles, going through all of those wires, you know what I mean? All of those cables, those huge towers with cables strung across. Now, if it's AC, it's going to be fluctuating positive, negative, positive, negative. That means that it's going to be a lot less friction on them instead of just being like on a speedway. So therefore, you can use thinner wires. It's also safer in case we happen to touch it, because it's not just direct pressure of electrons flowing through your body, it would be alternating. The other thing is, as I mentioned before, each country has adopted their own standard voltages out of the wall. And I always thought it was a little odd, because you go to Europe, you got to get an adapter, it's like different than American standards and all that. And I just chalked it up to the fact that in England they drive on the other side of the road, everybody's got their own thing. But actually there's a real reason why in Europe they use 220 or 240 volts and we use 110 at 60 cycles per second. They use 220 at 50 cycles per second. Now the reason is that when you think about all of the power distribution of going, in a city from the main power plant to all the little substations to the houses and so on and so forth. And we talked about what power is, because essentially at the end of the day, we want to turn on a light bulb, which is 100 watts. use some power. So if we have 100 volts coming out of the wall and we've got 100 watts of work we want to do, that would mean we need 1 amp of current flow, right? 1 times 100 volts would be 100 watts. Now in Europe, if we wanted to do 100 watts of work and we had 200 volts coming out of the wall, we would only need a half of an amp of current flow. So less current flow, meaning less electrons flowing through the wire, means that the wires don't get as hot, right? There's less friction, and therefore they can use thinner wires. And if that happens, then it's much cheaper and easier to do power distribution than it is to use thicker, heavier, more conductive wires. I hope that makes any sense to anybody. But it dawned on me that there's a real reason why everybody chooses a different standard. I wish we could get it like one world standard, that'd be nice. But unfortunately, it's never like that. Now there's one key issue that we didn't discuss in terms of electronics that I think is very critical. For example, we discussed what potential is, but it has to be potential related to what? Related to a baseline of no volts. So if we're talking about volts being a potential difference in the amount of electrons that it would make move, we have to basically have a reference of what 0 volts is. That's where we get to ground. It's called ground because it's 0 potential. It's our reference potential, and it's usually tied to Earth, believe it or not. Ground is ground, and all of these terms started, I think, when Benjamin Franklin was, lightning and all that, the potential out of lightning and Earth. And the reason lightning actually hits Earth is because it's going towards a 0 potential when there's a potential in the clouds in a storm of a voltage, a static potential, and then you get a lightning crack and it hits Earth because Earth is 0 volts. It's kind of like that water flow thing. Really, when it gets to a certain point, even if there's a blockage in your pipe, if you get high enough, it's going to be enough pressure that it's going to break through the blockage in the pipe, and it's going to go to the lower value. So all electrons always strive to go down to 0 volts, 0 potential. So ground is another term that's really, really important, and we'll discuss it as to how it's involved in making your sound system quiet, making your speakers not buzz. Why is there a buzz in my microphone? We can get rid of all that if we understand what ground is and what stray potential is. That's why I'm going through all this, not just to bore you, since I know you guys aren't electrical engineers.